So in the last video, we discussed about the phasor measurement unit and we discussed the internal architecture of the phasor measurement unit. Let's talk about the phasor data concentrator and see how the hierarchical network of phasor measurement unit is developed. So we will see in the field, we will have various PMUs installed at the buses. So the aggregation of the data happens with the help of phasor data concentrator. What is the role of phasor data concentrator? Phasor data concentrator takes the data of different PMUs and then it time aligns their phasor data so that we get the one single snapshot of the data set which is being provided by the PMU. So the main role of PDC is to time align the data and filter out the measurement data which is coming from the field. So after the PDC, we might have super PDC also, which can take data from multiple PDCs and then again it will time align and filter the data for further processing. So we can now assume that this PDC may be residing in one substation and then super PDC may be at the sub LDC control center and then we have the network of super PDCs which are installed at various levels, say at SLDC or the regional load dispatch center level, where they interact with each other to consolidate and aggregate the data of all the PMUs which are connected in the system. So this is how the hierarchical network of phasor data is being maintained. Now let's talk about the effect of nominal frequency. So nominal frequency is generally 50 Hertz for India and for US it is 60 Hertz. Now suppose if the frequency changes from 50 Hertz to 51 Hertz, so this 51 Hertz will become off nominal frequency. Then what will happen to the phasor data? Let's try to understand. Let's assume that the PMU data reporting rate is 10 frames per second. That means every second we are generating 10 data frames from the PMU and sample the data with nominal frequency. Then if the frequency changes from 50 Hertz to 51 Hertz, what will happen to the phasor data? Say at time 0, where we are getting the first frame. So at that point, if we have nominal frequency, we may get the phasor value as Vm by root 2 angle 0 degree. So for the off nominal also, it will be same. That means both are coinciding at time t is equal to 0. Now when we take first sample of the measurement, the nominal frequency angle will remain 0 degree because frequency is same. But what will happen in case of off nominal frequency? The angle will rotate by 36 degree. Why it will rotate by 36 degree? Because the fraction of second for first sample will be 0.1 second. So over a 360 degree plane, if the fraction of second is 0.1, that means the angle shift will be 36 degree because in one particular second we have one extra wave of 51 hertz signal. So what will happen in that case? That wave will correspond to 360 degree of the shift. So in that case, the 0.1 second will give you an advancement of 36 degree. 0.2 second will again give you the advancement of 72 degree and so on. So what will happen over a period of 1 second, the 51 hertz signal will again coincide with the phasor value of nominal frequency, but in between it will rotate by 360 degree, or you can say 336 degree per frame. So if you sample the data with nominal frequency and you take the phasor value which is now at 51 hertz, that is off nominal frequency, on the phasor plane you will see that the phasor is rotating with these angle values. So the effect of off nominal frequency is that the phasor value will not be static, it will keep on rotating in the plane. Now let's talk about the Fourier series and Fourier transforms, because this will be a building block for finding out the phasor value with the help of sample data which we get as an output of the A to D converter in PMU, and then we'll see how phasor estimation happens with the help of discrete Fourier transform. So let's first try to understand the Fourier series. So Fourier series decomposes a periodic signal into primitive periodic components. So we can define Fourier series as xt is equal to a naught by 2 plus sigma k is equal to 1 to infinity ak cos k omega naught t plus sigma k is equal to 1 to infinity bk sin k omega naught t. Now here the a naught is nothing but 2 by capital T integral from t naught to t naught plus capital T xt dt. AK can be defined as 2 by capital T integral of t naught to t naught plus t capital T xt cos k omega naught t dt. Similarly, bk can be defined as 2 upon capital T integral from t naught to t naught plus capital T xt sin k omega naught t dt. So capital T is the time period and k ranges from 1 to infinity. Now let's define omega naught as 2 pi f naught. So we can write 2 pi f naught is nothing but 2 pi upon capital T, which is the time period, and f naught is the fundamental frequency. So omega naught can be written as the fundamental angular frequency. Now let's define omega k. Omega k can be written as k times omega naught, which is kth harmonic angular frequency for this periodic function. So based on these variables which we have defined, we can write the Fourier series as xt is equal to a naught by 2 plus sigma k is equal to 1 to infinity ak cos omega kt plus sigma k is equal to 1 to infinity bk sin omega k t. Now we can apply some arithmetics to further simplify this. So what we can write? We can take the sigma out. We can write a naught by 2 plus sigma k is equal to 1 to infinity ak cos omega kt plus bk sin omega kt. Now if we multiply and divide by root of ak square plus bk square, then we can write this the above expression as a naught by 2 plus sigma k is equal to 1 to infinity root of ak square plus bk square, and in the bracket we will have ak upon ak square plus bk square under root cos omega kt plus bk upon under root ak square plus bk square sin omega kt. Now let's assume that this is equal to cos theta k. Similarly, this, that is bk upon root of ak square plus bk square, can be simply written as sine theta k. Now this can be simplified as equal to alpha naught plus sigma of k is equal to 1 to infinity alpha k cos omega kt minus theta k. So this expression, that is cos theta k cos omega kt plus sin theta k sin omega kt, can be written as cos omega kt minus theta k. We will assume that root of ak square plus bk square is nothing but alpha k, and a naught by 2 can be simplified and be written as alpha naught. Now xt can be written as equal to alpha naught plus k is equal to 1 to infinity summation alpha k cos omega kt minus theta k. Alpha k is nothing but harmonic amplitude and theta k is the phase angle. So we can write theta k as tan inverse of bk upon ak, and alpha k, as we discussed, will be root of ak square plus bk square, and alpha naught is nothing but a naught by 2. So for kth harmonic frequency, what we can write? Xkt is equal to root of ak square plus bk square cos omega kt minus theta k. Omega kt can be written as 2 pi k f naught. So this will become cos 2 pi k f naught t minus theta k, and the complex form of this expression can be written as xt is equal to summation of k is equal to minus infinity to infinity alpha k e to the power minus j k omega naught t, where alpha naught is a naught by 2, alpha k can be written as 1 by 2 ak minus j bk, and alpha minus k is the complex conjugate of alpha k. So we can write 1 by 2 ak plus j bk. Now let's talk about the Fourier transform. So Fourier transform represent the signal as a weighted sum of an infinite number of sinusoids. So how we can represent it? The Fourier transform, that is xf, can be written as integral minus infinity to infinity xt e to the power minus j 2 pi ft dt. Xt is the signal, where the ejk, if we write in this form, that is nothing but cos k plus j sin k, called as Euler representation. What Fourier transform does? It transforms the arbitrary function into a single analytic expression. Spatial domain T is converted into frequency domain. The inverse Fourier transform, that is IFT, can be written as xt is equal to minus infinity to infinity xf e to the power j 2 pi ft df. Now, these 3 points you keep in mind, because this will help you to understand about the Fourier transform, as well as when we will discuss the phasor representation, you will utilize these properties. So a signal xt is said to be band limited if its Fourier transform is 0 for all b greater than f, where b is some positive number. P will be called the bandwidth of the signal. So any band limited signal must have infinite duration in time. That is, band limited signals cannot be time limited. Similarly, time limited signals cannot be band limited, and thus all time limited signals have infinite bandwidth. In the discrete space, how we'll define the discrete Fourier transform? Because discrete Fourier transform will be utilized in the phasor estimation, because we are getting sample at a regular interval. That is, we are getting sample in a discrete form. So we will utilize discrete Fourier transform to calculate the phasor. Now DFT is used when the limited number of samples needed over a window. DFT of a discrete signal, let's say xn over a window of capital N samples, can be defined as xk is summation of n is equal to 0 to n minus 1 xn e to the power minus j 2 pi by capital N k n. The value of k ranges between 0 to capital N minus 1. Similarly, IDFT, that is inverse discrete Fourier transform, can be defined as xn equal to 1 upon n summation over k is equal to 0 to n minus 1 x k e to the power j 2 pi by capital N k n, where n now ranges between 0 to capital N minus 1. Now, Fourier series alpha coefficient is linked with discrete Fourier transform, and we can define alpha k is nothing but DFT of a signal x, that is xk divided by capital N. Let's talk about the phasor estimation. So what does phasor estimation does? It utilizes the discrete Fourier transform to estimate the phasor. The harmonic term in the Fourier series, as we saw in the previous slides, we can write xkt is nothing but root of ak square plus bk square cos of 2 pi k f naught t minus theta k. The corresponding phasor value of the above term can be written as xk is equal to 1 by root 2 root of ak square plus bk square e to the power minus j theta k, or simply we can write 1 by root 2 ak minus j bk. So the fundamental phasor can be written as x1 is equal to 1 by root 2 a1 minus j v1. So this we can get from the discrete Fourier transform. We know that alpha k is nothing but xk by n. So for fundamental, alpha 1 can be written as x1 by n, where the a1 is nothing but 2 times the real part of alpha 1, and b1 is minus of 2 times the imaginary part of alpha 1. So when we calculate the discrete Fourier transform, the component which corresponds to x1 and we divide by capital N, we get the value of alpha 1, and based on that we can deconstruct the fundamental phasor, and when we put these values we get the phasor value.